Alright, so for today, let's start off with an idea that we had last time. Imagine we have two blocks. These are metal blocks, and they're sitting next to each other. And one of them has a high temperature, one of them has a low temperature, but they're sitting right next to each other, touching each other. And so, over time, the hot block will get colder and the cold block will get hotter, and eventually we can agree that they will reach some sort of equilibrium. Okay, they'll reach some sort of equilibrium temperature. Well, we have to think about the idea that the energy, I'll call this block A and block B. This is still A, this is still B. The energy of A plus the energy of B has to be constant. So energy of A and B to start equals the sum of energy A plus energy B to finish with. So basically, the idea here is that our change in the energy of A plus the change in energy of B has to equal 0, because as B gains energy, A has to lose it, and it can't, the total energy is the same. Now, it bears mentioning that this is one of our pretend systems where there's apparently no radiation or anything. It's like the only two items in the universe are these two metal blocks. So that's what we're talking about here. So where am I going with this? Well, what if we wanted to know, maybe we knew how much this temperature and this temperature were, and we wanted to know this temperature. So we knew the temperature of A and the temperature of B to start. We want to know what the temperature of them both are, to finish. Well, I'm going to go through a few more ideas. We know that in this case, the change in energy equals the heat, which equals mc delta T, the mass times the specific heat times the change in temperature. Well, we can take these two ideas together, and instead of change in energy of A, we can write ma Ca delta T A plus the mass of B, the specific heat of B, times the change in temperature of B equals 0. See, we just put this in there. So there's our fundamental equation. So I'm going to move this. Okay, now remember, we're wanting to find the final temperature here. I'm going to switch colors, just because. I want to find the final temperature. Well, remember, delta T means this. I really have MACA TAF minus TAI plus MBCB TBF minus TBI equals 0. Okay, now maybe this is actually the equation you need to make sure you have in your notes, because this equation, as long as we only have one unknown, this equation can be solved for anything. Yeah, that could kind of be a pain. The algebra is going to be kind of messy, but it's not going to be hard. So in this case, we're looking for the final temperature. Now remember that we said that this temperature is the same, both these temperatures are the same. So that means that we shouldn't actually have an A or a B, for TF. We should just have TF and TF. Again, why? Because we said that the temperature reaches an equilibrium. They have the same temperature at the end. So really it should be TF and TF. Alright, so we want to solve for TF. Gross. So we distribute. So we have MACA TF minus MACA TAI plus, I just distributed that, MBCB TF minus MBCB TBI equals 0. We want to solve for TF, so I'm going to get everything without a TF on the other side. So I'm going to say MACA TF plus MBCB, should be a capital C, CB TF equals, subtract or add this and this to both sides, equals MACA TAI plus MBCB TBI. And I'm getting kind of messy here, but it's just a lot of stuff to kind of fit in. Okay, solving for TF, I'm going to factor TF out here. I'll switch colors again. Factoring out TF, I get TF times MACA plus MBCB equals all of that. I'm not going to write that over again. Then I just divide by this sum, and I get TF by itself. And finally, I get TF equals this MACA TAI plus MBCB TBI divided by that sum, MACA plus MBCB. And that should be a subscript there, not a big giant capital B. Okay, this is not hard. It is sort of irritating. Okay, so that's how we would find TF. If we knew the mass of each, we knew the specific heat of each, we knew the temperature of each to start with, we could just plug in and get this. Okay, we assume in all cases that the final temperatures end up being the same. Well, I say that. You don't have to, but if we're trying to find the final temperature, we have to assume that they're the same. Unless they give you the final temperature of 1, maybe this was 72 degrees, and we want to know how much this one is, we can actually do that. Again, using this equation, it's possible as long as there's only one unknown.